In the last section, we had started reviewing functions which are multi-valued, and in particular, we looked at the following functions. One is square root of z, the other being log z. And to recall, if you look at the function square root of z, then if one encircles the origin in the complex z plane once, which means theta varies from 0 to 2 pi, square root of z is going to be square root of r e to the I theta by 2. So therefore, square root of z goes to minus of itself, and it does not come back the way z comes back. Therefore, one needs theta to go once more around the origin between 2 pi to 4 pi in order that square root of z returns to itself. So therefore, instead of thinking of, so for a given point in the complex z plane, which is separated by a factor of 2 pi, in the argument, square root of z is going to take two different values, and hence, which is plus square root of z and minus square root of z, and hence it is a multi-valued function. However, if we construct the following sheet, such that when you go around once around the origin, you go from the first sheet to the second sheet, and going around the second time around the origin brings you back to the first sheet. Then such a sheeted structure, known as the Riemann surface, and here is the Riemann sheets, you have two of them. Such a sheeted structure makes this function single valued. Now, it's not necessary, as we saw in the last section, that it's not necessary that you have such a finite sheeted structure. One can also have infinite sheets, for instance, with a log z. So just to make things concrete, let's look at the following example. And of course, what's important is that it's nice to think of this, so basically between z equal to 0 and infinity, which are the branch points, one has a cut which allows you to go from one sheet to the other. And so therefore, when this going around this cut, the function picks up different phases. So starting at 0, we see that the phase of the function for square root of z is 0. Here it comes to pi by 2. The function, the square root of z gets a phase of pi by 2, and finally when z goes through 2 pi, it picks up a phase of pi. Now one can ask, what happens to a function like this, z minus a into z minus b? Okay, I can write this as sum ra e to the I theta a over 2 square root of ra into square root of rb e to the I theta b over 2. Now, if I look at the complex z plane, these 2 points a and b, of course I've picked them up arbitrarily, so well I should, there's no reason why one of them is negative. So let's just pick A and B. These 2 points are the branch points, and between them one has a cut in order to keep them single valued. Okay. The way to see this is as follows. Suppose I take an arbitrary point in the complex plane. This is RA and this is the radius RB. Okay, so let's define theta A and theta B. So therefore this is theta B and this is theta A. Okay, so when the function, if we start at this point here, we see that both theta A and theta B would be 0, so the function is just square root of RA into RB. Now, as I move this function, as I move this point and come here to somewhere here, theta B is going to pick up a phase of pi, whereas theta A would have gone through, would increase and then come back to itself. So therefore, the function changes by, it picks up an overall phase of pi by 2. On the other hand, if we go all the way here, then both theta A and theta B is going to pick up a total phase of 2 pi, so the function itself picks up a phase of pi. The same thing happens just below here. On the other hand, if we approach below the cut, you see that the change, theta B comes back to itself, while theta A will pick up an additional phase of 2 pi compared to what it was here, so that the overall phase is a minus pi by 2. So you see, across this cut between the points A and B, the function picks up different values, and therefore it is such a function is a map from a Riemann surface to the complex plane. Let's look at another example just to warm up on the phases. Suppose my function took this structure, z minus a over z minus b. Once again, I want to write z minus a as Ra e to the I theta a and z minus b as Rb e to the I theta b. Then this one is Ra over Rb into e to the I theta a minus I theta b over 2. Okay. Now once again, one can figure out the phases that this function would take between the points A and B. The points A and B are the branch points, and there is a cut between these two points. Now, when you, if you start here, the phase of the function is 0. Of course, let's first once again put a point. This is Ra, Rb, theta A, sorry, this is theta B, and this is theta A. Okay. So now, when you arrive at a point here, theta B changes by pi, while theta A increases and then it comes back to itself. So therefore, the overall change in the phase of the function is minus pi by 2. On the other hand, when we come here, then both theta A and theta B would have gone through a pi change, and therefore the total phase of the function is 0, which is also true here. And when we come to this point here, then the function would have changed by a plus pi by 2. So this then, while theta B would come back to itself, theta A would have an overall change of pi, and hence there is a change of pi by 2 for the function. Okay. So once again, this is a because of this branch cut allows one to define functions which are single valued, and that's very important when one does integration. Now, just to recall how the log function looks like, we had this function log z, which one could write as log of r e to the I theta. Therefore, this was log of r plus I theta. This is again the definition on the principal sheet. Now, if theta is offset by a factor of 2 pi, then while z comes back to itself, log z now becomes log r plus I theta plus 2 pi I. And one more rotation, this one becomes log r plus I theta plus 4 pi I, and so on. So in general, after n rotations about the origin, this becomes plus 2 pi ni, and so on. So log, therefore, has a Riemann structure in the form of infinite sheets. N equal to 0 defines the principal sheet, and as mentioned in the last section, it's only on the principal sheet that log 1 is 0. Now, such functions which are multivalued have very different behavior when there are singularities. For instance, suppose one looks at this function 1 over z log of 1 minus z. Now, it looks like z equal to 0 could be problematic. So first, let's start by asking what we need to choose a sheet. So let's pick up the principal sheet. In the principal sheet, suppose we expand this function about z equal to 0, then we have 1 over z log 1 minus z minus z square, and so on. Now, log 1 is 0 on the principal sheet, so therefore this just becomes minus 1 plus terms of order z and higher, and therefore you see that this becomes a removable singularity on the principal sheet. However, if n is not equal to 0, log 1 is not 0 either. Therefore, this becomes a simple pole at the origin in any other sheet other than the principal sheet. Now, when one does contour integrations, it is important that the function comes back to itself, which is the essence of the Cauchy's integral theorem. And when one has a branch cut and when one circles a branch point, the function does not come back to itself. Therefore, it's necessary that one encircles the branch point enough number of times so that it comes back to itself, or choose a contour such that the function is always single valued. In the next section, we will see an example of doing a contour integral which has functions which are multivalued.